Now let us continue our discussion for lesson 3. We will discuss now the properties of matrix operations. First, we have the properties of matrix addition and scalar multiplication. If A, B, and C are m by n matrices, and C and D are scalars, then the following properties are true. First, the addition of matrices is commutative, that is, A plus B equals B plus A. We also have the associative property of addition. We have this one. So in here we group B plus C, and in here we group A plus B. Also, we have the associative property of multiplication. So notice how we move the parentheses. And then next, we have the multiplicative identity. So we have 1. So the scalar 1 multiplied by the matrix A is just A. And we have here the distributive property. For the scalar C, we multiply it by A plus B. So that is equal to CA plus CB. And then in here, we have sum of two scalars, C and D, then multiplied by the matrix A, that is just equal to CA plus DA. Next are the properties of zero matrices. So note that a zero matrix is a matrix containing 0 elements only. So if A is an m by n matrix and C is a scalar, then these things are true. First, the sum of an m by n matrix A and the m by n zero matrix is equal to A. Also, if A is added by the negative A, then it results to a zero matrix. And then the third one, if the scalar multiple of A by C is equal to zero matrix, it's a zero matrix, then either C is 0 or the matrix A is a zero matrix. Note that the zero matrix OMN, or this zero matrix, is the additive identity for the set of all m by n matrices. Now, let us solve for the matrix X given the equation 3x plus A equals B, where A and B are these matrices. So, by applying the properties discussed, we have, so given that we have 3x plus the matrix A equals B, this implies that 3x plus A plus, you can add negative A on the left side and also on the right side of the equation, we have that. So this implies 3x equals B plus negative A, because this becomes a zero matrix. Then it implies that 1/3, we multiply by 1/3, we have 3x equals 1/3 times B plus negative A, which implies x now is equal to 1/3 times B plus the negative of A. Okay, so now we substitute the given value, the matrix B and A here. So we have x is equal to 1/3 times negative 3, 4, 2, 1, then plus negative 1 times your A. 1, negative 2, 0, 3. Okay, and then let us simplify. So 1/3 times negative 3, 4, 2, 1. So this is a scalar this is A times the scalar -1. So we simply multiply these elements by -1. So we can have -1, 2, 0, -3. And then we add these two matrices. We simply add the corresponding elements or entries. We have -4, add this, we have 6, 2, and then -2. And then finally, you can multiply by the scalar 1/3. So our x now is equal to -4 over 3, 2, 2 over 3, and -2 over 3. Okay, so this is our x in the given equation. Next, we have the properties of matrix multiplication. If A, B, and C are matrices with sizes such that the given matrix products are defined, and C is a scalar, then the following properties are true. So we have the associative property of multiplication. So again, try to look at how we group these matrices here. So we have here the BC, and then we group here the AB. The distributive property for matrix multiplication. So we have A times the sum of B plus C. So that is equal to the product of matrices AB plus the product of matrices AC. And another distributive property coming from the right side. So we have here AC plus BC. And then for the last one, we have the product AB times the scalar C is just equal to, we associate this, so we group CA times B, and then we move C there, so that is just equal also to A times CB. Now note that in general, matrix multiplication is not commutative, and matrix algebra does not have a general cancellation property for matrix multiplication. That is, if AC is equal to BC, it is not necessarily true that A is equal to B. So for example, we showed that AC is equal to BC given the following matrices. So let us multiply AC first. Matrix A times matrix C, we have 1, 3, 0, 1 multiplied by 1, -2, -1, 2. So recall how we multiply matrices. So we first multiply the first row of the first matrix, which is A, times the first column of C. So we have, and then we add the result. So we have here 1 plus -3, or 1 minus 3. Next, we multiply this first row to this second column. So that is -2. Then the product of this is 6, so plus 6. And then this second row multiplied by this first column. So that would be 0 plus -1, or 0 minus 1. And then this second row times the second column, which is 0 plus 2. Now to simplify, we have this. This is -2, 4, and then -1, +2. Okay, so that is the product of A times C, or the product of matrices A and C. Next, let us solve for the product BC. So these two, we have 2, 4, 2, 3, multiplied by 1, -2, -1, and then 2. So again, the same process. We multiply this by this, and then we add the result. So that's 2 minus 4 to this one to this one. So that's -4 plus 8. Then this row to this column, we have 2, -3, and then this to this one, we have -4 plus 6, which is equal to, we have -2, this is 4, This is negative 1, and then this one results to positive 2. Okay? So from our solution, we see that AC is equal to BC. But take note that we have AB is not equal to A rather is not equal to B. So in general, cancellation of this matrix C doesn't hold true. Okay. Next, we have the identity matrix. The identity matrix of order n is a special type of square matrix that has ones on the main diagonal and zeros elsewhere. It is usually denoted by I sub n. So this is how it looks like. So this matrix IN serves as the identity for matrix multiplication. That is, if A is a matrix of size m by n, then the following properties are true. So any matrix multiplied to the identity matrix is just equal to the matrix itself. Or for number 2, the identity matrix multiplied to a matrix A is just equal to A. But take note of the size. It should be that the multiplication must be defined. Now, for repeated multiplication of square matrices, we use the same exponential notation as what we use with real numbers. That is, A raised to 1 is just equal to A, and the square of the matrix A is just equal to A times A, and A cubed is just equal to A times A times A. And for any positive integer k, your A raised to k is just equal to A times A with k factors. It is convenient also to define A raised to 0 as the identity matrix, where A is a square matrix of order n. These definitions allow you to establish the properties. First, your A raised to j multiplied to A raised to k is just equal to A raised to j plus k. So we add the exponents. And for A raised to j and then raised to k, that is just equal to A raised to j times k, where j and k are non-negative integers. For example, for this given matrix A, let us find A cubed. That means we want to get A times A times A. We have A cubed equals A times A times A. So this is equal to, our A is 2, negative 1, 3, 0. So multiplied by itself, and then multiplied by 2, negative 1, 3, 0. Okay, so let us solve this first. So we multiply these first two matrices. So this is first column times first row rather times the first column. So we have 4 minus 3, so that's 1. We have the first row times the second column, that's negative 2. Then second row times the first column, so that is 6. This second row multiplied to the second column, so we have negative 3. And then we multiply by 2, negative 1, 3, 0. So that is equal now to the same process. We have 2, negative 6, so we have negative 4. We have negative 1, 0, so that's negative 1. We have 12 and then negative 9, so that's 3. And then we have negative 6. Okay, so our A cubed is equal to negative 4, negative 1, 3, negative 6. Next, we have the transpose of a matrix. The transpose of a matrix is formed by writing its columns as rows. For instance, if A is the m by n matrix, Then its transpose, denoted by AT, is the n by m matrix given as this one. So what happened is the first row or the rows of A is written as columns of A transpose. So we have this written as column, this one, this row here, again we write it as the column of the transpose to get the transpose rather. Now we have the properties of the transpose. So first, if A and B are matrices with sizes such that the given matrix operations are defined and C is a scalar, then these properties are true. Number one, the transpose of A is just A. Next, the transpose of the sum of matrices A and B is equal to the sum of the transposes of A and B. Also, the transpose of the scalar multiple of A by C is equal to the scalar multiple of A transpose by C. And lastly, the transpose of the product AB is equal to the product B transpose times A transpose. The proofs of this will be left as exercise. Now we have the definition of a symmetric. So a matrix A is called symmetric when A is equal to its transpose. Note that if A containing Aij is a symmetric matrix, then Aij is equal to Aj for all I not equal to j. For example, if A is a 3 by 3 matrix, say A is equal to 1, 3, negative 1, say 3, negative 4, 2, negative 1, 2, 0. Now, if we get its transpose, we have, again, you just write the rows of A as columns. So we have now this row, 1, 3, negative 1, negative 1, and then the second row, we write it as second column. So we have 3, negative 4, 2, and then last one, we have negative 1, 2, 0. Now notice that the result when we get the transpose of A is just equal to A. So we have A is equal to A transpose. Since the entry A12, for example, is equal to A21. So we have this A12 is just equal to this entry A21 here. Then also, your A13 is just equal to the entry A31. Then for this entry here, that's A23, is just equal to A32 entry. Okay, so for all I not equal to j, ij is equal to aij rather is equal to aji. For all I not equal to j. Next, we have here an example. So we will show that the transpose of the product AB and B transpose times A transpose are equal. So we have the given specific matrices A and B. So we have here the solution. So if we multiply A and B, we have this matrices. The product will be this one. And then if we get the transpose of the product AB, again, we write the rows as columns. So we have 2, 1, then 6, negative 1, and then we have negative 1, 2. And also, for the transposes of B and A, so this is B here. So remember, this is a 3 by 2 matrix. So its transpose must be a 2 by 3 matrix. So we write these rows as columns and so on. And also this A here, we write these rows of A as columns here. So we have negative 1, 0, 3, 0, negative 2, 1. So when we multiply these matrices, we have a 2 by 3 and a 3 by 3 matrix. So its product must be a 2 by 3 matrix. So when you multiply, you can check this one. The result will be this. And notice the two results we have. If we get the transpose of this product, again, we have this, is just equal to the product of B transpose times A transpose. Another example we have for the matrix A equals this matrix. Find the product A transpose and show that it is symmetric. So what we do is first we find or we get the A transpose. So an A is a 3 by 2 matrix. So we will have a 2 by 3 matrix here. So we write the rows as columns. So we have 1, 3, 0, negative 2, negative 2, negative 1. Okay. And then next, we get the product of this. So we multiply A by its transpose, negative 1. So this is equal to, so we are expecting a 3 by 3 result because this is a 3 by 2 and then 2 by 3 matrix. So it must be, the result must be a 3 by 3 matrix. So we multiply, we have here, this is 1, 9, so we have 10. We multiply this first row to the second column, so that's negative 6. We have negative 2 and negative 3, so we have negative 5. We have 0 and negative 6. We have 4, 0. We have here positive 2. And then the last row to each column, so we have negative 2 and negative 3, so negative 5. And then negative 2, we have positive 2. And then we have positive 4 plus 1, so that is 5. Okay, and then next is we will show that this is symmetric by you can show that A transpose is equal to its transpose. So we have that one. Okay, so we have, this is our A transpose, so we get the transpose of this equal to 10, negative 6, negative 5. So we write this row as column here. And then we have negative 6, 4, 2, negative 5, 2, 5. Okay, so which is exactly equal to or the same with A transpose. Or another way is just to observe the entries here. Notice that for this, for each I not equal to j, Aij is equal to Aji. That is, this entry is equal to this entry is equal to that, and this to that one. Okay, so therefore we say that A transpose is symmetric. So note that for any matrix A, the matrix A transpose is symmetric. The matrix A transpose A is also symmetric. Okay, so that's the end of our discussion for lesson 1.3, the matrix operations and their properties.